So I'm going to draw a picture of what this looks like. You may not really know if you haven't seen this picture before, but we'll have a horizontal surface, and we're going to have an object. It's 5 kilograms, and it's going along the horizontal frictionless surface in this case, and it's going to reach a point where it's going to run into a spring that's actually perfectly positioned horizontally. So it runs into a spring, and it's going to squish the spring, and it's going to reach some kind of a maximum. Like at some point, the spring will bring the block to rest. But that's only going to be for a moment. Afterwards, the spring's going to actually push it back, and the block's going to slide backwards after that. But that's not part of the problem. The problem is only to determine this moment of maximum spring compression. So we have to analyze it at one specific moment. And that's going to happen with the conservation of mechanical energy. We do not have to worry about non-conservative forces since there's no friction. Then there is a normal force, but it's always 90 degrees to the motion, so it's doing zero work on the object. There's no applied forces, so yeah, we will use the conservation of mechanical energy. So I'll write the long version of that, which means I would say the sum of the kinetic and potential energies will equal to each other before and after. However, I'm going to skip over gravitational potential energy altogether and just focus on kinetic and spring, because this object is not moving up or down. There's no change in gravitational potential energy during this situation. There's no need to have this in our formula. Okay, so kinetic 1 plus spring 1 equals kinetic 2 plus spring 2. And you're going to analyze and ask if any of these is going to be 0. Well, actually, a couple of them are. Before this block even makes it to the spring is just sitting there at rest in its natural position. So there's no spring energy before the block hits it. So that's 0. And at the moment of maximum spring compression, the block will be brought to a rest for an instant at that moment. But that means we can make K2 0 because it comes to rest for that moment. So actually that simplifies our equation quite a bit. It's just one energy equaling another. So what's actually happening in the situation, being nice if you wrote this on your problem sets for similar situations, is basically all of the kinetic energy that the block has at the beginning is going to be transformed into elastic potential energy, 100% of it. Formula-wise, kinetic energy is half mv squared. Elastic potential energy is half kx squared. So the halves cancel out. And we are solving this for the maximum amount the spring will compress. So we are solving this for x. So I'm going to go ahead and isolate for x there. So I'm going to divide by k and then square root both sides. I'm going to skip the step of writing plus or minus, with the negative being inadmissible. Well, I chose some pretty nice numbers here. 10 squared is 100. So 100 divided by 100 is 1. So it's really just going to be the square root of 5. But I still have to put that in the calculator. And round it to 2 sig figs, giving me 2.2. So that's a long spring. So I chose some bad numbers here, pretty much. Probably should have made the spring stiffness 1,000, something like that, or 2,000 even. Yeah, that's a pretty weak spring, actually, to try to stop a 5-kilogram object that's going at 10 meters per second. But that's what the math works out to be, so we'll just imagine we have springs that long that do that, and that's how you solve it.